Hello. So, today we are going to talk about modeling of damping in a multi-degree of freedom system. So, we have talked about modeling of damping in a single degree of freedom system. So, just to give a brief recap, we have talked about linear viscous damping, we have talked about dry friction damping or Coulomb damping, we have talked about other forms of damping that may occur in a single degree of freedom system. So, when we move to multi-degree of freedom system, the same theory and the same type of damping will also exist for a multi-degree of freedom system. So, usually what happens, as we have discussed in detail, a multi-degree of freedom system can be considered as a combination of several normal mode of vibration. So, each of this normal mode of vibration is kind of a single degree of freedom problem. So, the way we have dealt with modeling in a single degree of freedom problem, that same thing can be translated to a multi degree of freedom system and in a normal mode context. So, for each normal mode we can again consider a viscous damping or a dry friction damping or hysteretic damping, etc. So, now what we are going to talk about in this lecture is how to model damping in the context of a multi-degree of freedom system. In multi-degree of freedom system, we have talked about how to find out the mass matrix, the stiffness matrix, how to find out the natural frequencies, the mode shapes, how to use the modal expansion theorem or modal superposition using to obtain the response of a system. Now, we will see how are we going to model damping in this context. So, the theory and other experimental determination of damping will remain exactly similar to what we did for a single degree of freedom system. What we are going to change here is how to translate this information and model them properly in a multi degree of freedom system. So, the most common form of damping in a so let us first talk about proportional or Rayleigh damping. So, proportional or Rayleigh damping is the most common form of modeling of damping in for a multi degree of freedom system. So, what we do is that suppose we have a MDOF system with n degrees of freedom. So, my M and K matrices are n cross n. So, this is n cross n and my K matrix is also n cross n. So, suppose I want to introduce damping into the system. So, all this while when we discussed about multi degree of freedom system, we discussed only about undamped system, we did not bring in damping anywhere, but damping as it was important in a single degree of freedom system, it is equally important for multi degree of freedom system. So, now from a multi degree of freedom system, if we the one most common way of introducing damping is to add a C matrix to the equation of motion. So, if we have an n degree of freedom system, we will introduce a stiff damping matrix C, which is going to be n cross n. So, the damping matrix C can actually be written as some constant alpha into the mass matrix plus some constant beta into the stiffness matrix. This alpha and beta are called the proportionality constant. So, this is a very simple form of damping. Modeling of damping for a multi degree of freedom system. So, if we have a system like this, what we are going to have, the equation of motion is going to be m u double dot plus c into u dot plus k into u is going to be f. So, this is what the equation of motion is going to look like. So, if we have used proportional damping, this equation m u double dot plus C can be written as alpha into M matrix into u dot plus beta into K matrix into u dot plus K into u is going to be equal to f. So, the only thing, so M and K matrix are known. So, the only thing that we have to figure out to do such proportional damping modeling is this proportionality constant alpha and beta. Now, how to find out alpha and beta we will talk about a bit later. Right now, let us see what is the advantage of modeling the damping matrix in this form. So, if I have modeled this, then my equation of motion is going to look like this. Now, if this is the equation of motion, then I have m into u double dot plus alpha into m into u dot plus beta into k into u dot plus k into u is equal to f. Now, if I do modal transformation to this, if I write the degrees of freedom u in terms of my natural coordinate or generalized coordinate as phi into eta, where phi is my modal matrix, the same old thing that we had done earlier. So, this is mass normalized modal matrix. And this is the natural coordinate or the generalized coordinate. Now, as we have done earlier, if I plug this into this equation of motion, what am I going to get? I am going to get phi transpose m phi into u double dot plus alpha into phi transpose into m into this is going to be eta double dot into phi into eta dot plus beta into phi transpose into k into phi into eta dot plus phi transpose into k into phi. So, this can actually be written as eta double dot plus alpha plus beta into omega square, omega p square, where p is varying from, into eta dot plus omega p square into eta is equal to Q P, right. So, this is the equation that I am going to get after converting it into the natural coordinate or the generalized coordinate. Now, you see that alpha plus beta omega p square that we are getting can always be written as eta double dot plus alpha plus, instead of alpha plus beta omega square, I can always write this as 2 zeta p into omega p, and therefore, this is going to become 2 zeta p omega p. So, sorry, this is going to be a diagonal matrix with the diagonal terms as this. Sorry about this. Zeta p into eta dot plus, again this is a diagonal matrix with the diagonal term as this, and this is going to be a diagonal matrix with omega p square into eta is going to be Q P T. So, I can even drop the matrix thing and I can write this as eta p double dot plus 2 zeta omega p into eta p dot plus omega p square into eta p is equal to Q P T, where p is 1 to n. Now, what is 2 zeta omega p? 2 zeta omega p is alpha plus beta into omega p square, right. So, I can solve this equation very easily. I know how to solve this equation. For even any given value of QPT or any given value of f from where we can find out the value of QPT, I can always solve this equation. This is nothing but it just look like a single degree of freedom equation, which is very easily solvable. I know all the methods to solve this problem. So, I can solve it. So, only thing that I am not known here is zeta p. Okay. So, how is zeta p related to alpha and beta? 2 zeta p omega p is actually equal to alpha plus beta omega p square. Now, I do not know alpha and beta. I actually do not know alpha and beta. Now, my job is to find out alpha and beta, and if I know alpha and beta, I can always find out zeta p or vice versa. Now, what do people do in real life case? In real life case, when you have a multi-degree of freedom system with say 5 degrees of freedom, then people excite each degree separately. Excite as in they make the system vibrate only in the first degree of freedom system or in the second degree of so if there is a 5 degree of freedom system, what is done experimentally is that the system is made to vibrate in its first normal mode. So, when it is made to vibrate in its first normal mode, it vibrates with the first natural frequency, and when it is vibrating in the first natural frequency, by using experimental technique like logarithmic decrement, we can find out the damping factor zeta 1 for the first normal mode. So, when it is vibrating only in the first normal mode, it is vibrating like a single degree of freedom system. So, we know how to find out the damping factor for a single degree of freedom system. So, we will find out the damping factor for the first normal mode for this 5 degree of freedom system. So, let me call zeta 1 to be the damping factor for the first normal mode of the 5 degree of freedom system. Similarly, I can make the system vibrate only in a second normal degree of normal mode of vibration, and say zeta 2 is the damping factor for the second normal mode of the 5th degree 5 degree of freedom system, 5 or n, I am just taking 5 as a number, 5 or n degree of freedom. So, once I get zeta 1 and zeta 2, then I will have two equations in hand. I will have 2 zeta 1 omega 1 is equal to alpha plus beta omega 1 square. This is my equation number 1, and then I will have 2 zeta 2 into omega 2, which is the second natural frequency, that is going to be alpha plus beta into omega 2 square, again my second natural frequency. So, from these two equations, since I know zeta 1 and zeta 2 experimentally, so zeta 1 and zeta 2 are known experimentally. Say by using logarithmic okay. So, once I know zeta 1, zeta 2, omega 1 and omega 2 are already known. So, by solving these two equations, I can get alpha and beta, and therefore, I can get the proportionality constant. Once I get the proportionality constant, I can write my damping matrix as alpha into m plus beta into k, and go ahead with the modeling of the system and solution of the system using modal analysis. Now, there is one drawback of this modeling technique for damping. The drawback is that my alpha and beta are determined by only two damping factors. So, if I have to fit in more damping factor, say suppose I have 5 different damping factor for the 5 normal modes of the 5 degrees of freedom system. So, this proportional damping model cannot take into account all the 5 damping factors. It can take into account only 2 of the damping factors. So, it can give you the damping factor correctly or as measured in the experiment only for 2 normal modes. The damping factor for the other normal modes will be automatically derived and you cannot have a handle on it. So, let me just summarize this. So, C in proportional damping can be written as alpha into m plus beta into k. So, alpha and beta are proportionality constant. Alpha and beta can be obtained from the damping factors zeta 1 and zeta 2, which can be measured experimentally for 2 normal modes of the system. The advantage of using proportional damping is that the modeling of proportional damping allows doing modal analysis of a multi-degree of system. So, this model of damping matrix very easily allows us to implement the modal analysis. So, if C was not of this form, then I could not have derived a simple equation of eta double dot p plus 2 zeta omega p into eta p plus omega eta dot p plus omega square eta p is equal to q p. This simple single degree of freedom like equation that is derived from the matrix equation of the multi degree of freedom system is not possible if the damping is of some other form apart from this proportional damping, and that is why this proportional damping model of proportional or Rayleigh model of damping has become so popular and is a very conventional or common method. Several commercial packages actually adopt actually has option for modeling damping in form of proportional damping. They actually ask only the proportionality constant and they model damping using this technique. Now, one more thing that I wish to talk about proportional damping is that the proportionality constant alpha and beta, which are determined in terms of zeta 1 and zeta 2, we should remember that the value of alpha is more, whereas the value of beta is less, because beta is associated with omega square. So, we have seen that 2 zeta p omega p is equal to alpha plus beta into omega p square. So, the contribution of beta is much more on zeta p than alpha, because beta is associated with omega p, which is usually a large number. Therefore, the contribution of beta is much more on the proportional damping than alpha. So, usually the value of alpha is more and the value of beta is a lesser number. So, with this we are going to move into an example problem that we will solve to get the concepts more reinforced. So, let us consider a 3 degree of freedom system whose mass and stiffness matrices are given of this form. So, the 3 natural frequencies already have been derived and the values of the natural frequencies are given as follows. We can also find out the natural frequencies very easily on our own, this natural frequency, but they have been predetermined just to decrease the time taken to solve the problem. So, the problem statement is somewhat like this. So, it says that it has been found experimentally using logarithmic decrement that the damping factor for the first 2 mode is 5%. So, you need to find out the proportionality constant alpha and beta accordingly. Okay. So, how are we going to solve this problem? So, it is given that zeta 1 is 5%, zeta 2 is also 5%. Okay. So, now I know that 2 into zeta 1 into omega 1 is going to be alpha plus beta omega 1 square. So, let me put the values for omega 1 and zeta 1. So, 2 into zeta is 5%, so 0.05 and omega 1 is 0.134 into root over k by m, and that is equal to alpha plus beta into omega 1 square, which is 0.134 whole square into k by m. So, this is equation 1 that we have. So, the equation 2 gives me 2 zeta 2 omega 2 is equal to alpha plus beta into omega 2 square. So, that gives me 2 into So, now if I subtract equation 1 from equation 2, I can remove alpha and the value of. So, what I do is that I subtract equation 1 from. So, if I do that, alpha is eliminated and from that I will get the value of beta equals to 0.088 root over k by m. So, once we get the value of beta, I can solve for alpha and alpha comes out to be 0.12 root over k m. So, this is the answer for the problem. So, the proportionality constant are alpha equals to 0.12 k by m root over k by m and beta is equal to 0.088 root over k by m. Now, once this alpha and beta are already calculated based on zeta 1 and zeta 2, then automatically my damping factor for the third mode, if I call it as zeta 3, then 2 zeta 3 into omega 3 becomes automatically alpha plus beta omega 3 square, which gives me 2 into zeta 3 I do not know, omega 3 is 1.866 root over k by m, that is going to be 0.12 root over k by m, and then I have, sorry, this is root, sorry, this is m by k. So, plus 0.088 root over m by k into omega 3 square. Okay. So, from this we can get the value of zeta 3, which is equal to 0.12 k by m plus 0.088 into 1.866 square into k by m divided by 2 into 1.866 k by m. So, this is going to be the value of zeta 3 irrespective of what is the value of zeta 3 physically. So, physically we may obtain the value of zeta 3. So, from experiment we can always obtain the value of zeta 3, which could be say 4%. But based on this modeling, the value of zeta 3 is fixed. The value of zeta 3 is obtained from this calculation and that value is fixed. So, I actually cannot capture the real value of zeta 3 which is obtained from experiment using this model, though I have captured the real value of zeta 1 and zeta 2. but I cannot capture the real value of zeta 3. So, that is one of the drawback of the system, but since usually the first two modes matter most when we are dealing with a real case. In most of the real cases, the first two modes are the most important mode, most dominating mode. So, often if we model the damping for the first two mode correctly, it is enough to obtain an accurate solution of the problem. The other thing is that the damping factor usually for different normal modes usually do not vary much, and therefore, a small variation from the actual damping factor may not influence the response to a great extent. So, with this we are going to end this lecture. In the next lecture, we are going to talk about rigid body modes of a multi degree of freedom system. Thank you.